So today I want to talk to you about the slit ventricle syndrome. And you don't have to know everything about slit ventricles, but you have to know a little bit in neuro-ophthalmology because it comes to us. So the slit ventricle syndrome is the opposite of ventriculomegaly and hydrocephalus. So when you have a scan and you have big ventricles, that's hydrocephalus. That can be obstructive or communicating or non-communicating hydrocephalus. So when we see hydrocephalus, the things that are going to come to us are papilledema, the swollen disc from increased ICP, the dorsal midbrain syndrome, and the non-localizing sixth nerve palsy. They're going to have symptoms of increased intracranial pressure, headache, tinnitus, double vision, loss of vision. And normally the hydrocephalus cases are pretty straightforward. If they already have a shunt in place, it's shunt failure until proven otherwise. So the normal scenario that we see is big ventricles, shunt failure, or needs a shunt. Signs and symptoms of increased intracranial pressure. However, sometimes the ventricle is not big, it's small. This is called the slit ventricle syndrome. And the slit ventricle is usually because they already have a shunt in place and the ventricle has collapsed. In this setting, the slit ventricle syndrome, that's normally from chronically shunted hydrocephalus, previous hydrocephalus that they shunted. And we're going to be looking for the same symptoms and signs of increased intracranial pressure. And normally you would expect if they've got a shunt in place that it would be overdraining and that we'd have too low of an intracranial pressure. And so we have competing hypotheses with the slit ventricle. Normally it's overdrainage and your ICP is too low, but sometimes the pressure is still too high. And the reason is the compliance has been lost here in the ventricle, so it can no longer expand, or the law that you're familiar with already on the other videos, and you can rewatch those, the law of Laplace. So in the law of Laplace, the tension equals the pressure times the radius. And you know that if you've ever tried to blow up a balloon when it's flat, it's hard because the radius is so small. So the amount of P, pressure, necessary to blow up a flat balloon is a lot higher to overcome the elasticity of that balloon. So in order to generate enough T so that the balloon will expand, just like the ventricle has to expand, to make the radius go up, we have to use a lot of P, air pressure, at the beginning of blowing up the balloon. And what that means for you is if the ventricle is already slit, that means the radius is already small. And that means the amount of P, intracranial pressure, to generate sufficient T, wall tension, to expand that, is going to be greater. And that means there's a competing hypothesis on the slit ventricle. It doesn't have to be over drainage. It could actually be under drainage, that your pressure is actually high, but insufficient to generate enough P to get this T go up because the R is so small. And that means shunt failure. And so we cannot rely upon the CT scan alone to tell us what the function of the shunt is, and especially in the setting of a slit ventricle. You're going to do a shunt series, which is just a series of x-rays to make sure it's not disconnected. But if it is connected and you still think it's failed, the only way to know is to put dye into the shunt, called a shuntogram. Technetium is normally what we use to see if the shunt is broken, and the only way to measure the pressure is to have a spinal tap. So you need to know that the big ventricle syndrome is easy, and the bigger ventricle syndrome is hydrocephalus or shunt malfunction, but the slit ventricle is hard. And the reason it's hard is it could be too much drainage or it could be too little drainage. And if it's too little drainage, it's because of the law of Laplace.